So today we're going to be looking at how we can use the SRK equation of state to plot some isotherms for water. First off, I already did some of the housekeeping things. Here we're just bringing in this GitHub repository with some data and some tools to use with a bunch of substances, namely water in this case. Here we're just telling the coding environment here that we want to search in this file path for our tools. Here we're just renaming some things. We're using the tools pack from this repository up here, and we are also going to use NumPy from SciPy Optimize. We're going to be using root. We're going to use the make subplots function from Plotly. This function here from SciPy integrate the quadrature function. We're actually not going to be using in this video. We're going to be using it later on to dealing with Maxwell constructions, so we can go ahead and comment that out. And then we're going to import Plotly as PO, and finally we have just a dark template for our plots. And then, of course, our R value, which we are going to be using often. So first off, looking at our SRK equation, we have some parameters and some constants that we need to solve for, A, B, epsilon, and sigma. So we're going to create a function to return this. So if we start off with, we'll just call it cubic ABES, and then our input is just going to be a temperature. And we want it to return our A, B, E, and S, or A, B, our epsilon and our sigma, with B being the excluded volume and A being the parameter for attraction. So we can start off with our temperature, our reduced temperature is going to be equal to our temperature critical, or our temperature divided by our temperature critical. And actually I did forget to instantiate our tools here. So let's go ahead and bring that up. You know what? There we go. And then P will just be our CHE, or our tools. Sorry about that. Our instantiation of props. And then obviously we want water. There we go. And then let's just double check that. There we go. And then we're also going to need a few values, and I have them over here to reference because there's no way I'd remember these. So we're going to need omega, and that's going to be equal to 0.08664. So we'll go ahead and paste that in. And we're also going to need psi, which will be 0.42748. And then we're going to need to calculate alpha, which we'll use in our calculation of the parameters A and B. Actually, it won't be used in B. But alpha is equal to this equation here. And I'll go ahead and go through this. So we have 1 plus 0.48 times 1.574 times, this is omega as well. And this is the eccentric factor for water. So again, we're bringing that in with the P.W. Minus 0.176 times our omega squared times 1 minus our reduced temperature to the 1/2, or the square root of, and then this whole thing squared. So next up, we need to calculate our parameter A, and A is equal to psi times our alpha times our R value squared, which we brought in all the way up in the beginning, and then times our critical temperature, also squared. And then all that divided by our critical pressure. And then finally we can define, well, not finally, but we can define our B value, or our excluded volume, as omega times our R value times our critical temperature, all divided by our critical pressure. And then epsilon and sigma are pretty easy as well. They're just constants. In this case, epsilon is going to be 0 and sigma is going to be 1. So if we go ahead and double check, go ahead and test this out. And we'll test it out at a temperature of, say, 300 Kelvin. So here we have our A value, our B value, so our constant for attraction, our parameter for the excluded volume, and then our constants. So now that we have our function for finding our A, B, epsilon, and sigma, we can go ahead and make a function to find the cubic pressure. So we'll make another function, and our inputs are going to be a specific volume and a temperature. And we want it to return our pressure, obviously. I forgot a colon up here. So we're going to need these A, B, epsilon, and sigma values. So to bring those in, we can actually just calculate, given or using the temperature that we give it, we can calculate the values using this function up here. So we'll say A, B, epsilon, sigma are equal to the result of our cubic ABES function using the temperature that we input. And then the formula for pressure is pretty simple. Pressure is equal to R times temperature divided by the volume minus the excluded volume. And then all that minus the parameter for the attractive force divided by the result of multiplying our volume plus the epsilon times sigma, or epsilon times B, with the term volume plus sigma times B. Everything looks good there. Okay, and then if we want to test this out, we can test this out at a, we'll say a specific volume of 1e minus 3 cubic meters per mole, and then at a temperature of 300 Kelvin, not 3000. All right, so this is our pressure given, and this is in pascals. This is our pressure in pascals using this specific volume and this temperature. And it does that by, again, calculating the A, B, E, and S using the temperature that we give it using this function up here, and then just plugging those values into this formula right. So we're almost ready to get started plotting, but before we do that, we have to define our x-axis or our v, and we have to come up with a function to give us a bunch of values for our specific volume to plot with. So we'll start off with a lid space, and I'm going to do this wrong intentionally so I can explain a few things. And so here we're saying we want to start out at 0 cubic meters per mole, go all the way up to 300, and we want 500 steps in between. So the issue with this is, first off, our range here isn't very good. A more accurate range would be somewhere around 0 to 1 E4 cubic meters per mole. And the other issue here is that we only have 500 increments to get from 0 cubic meters per mole all the way up to 10,000 cubic meters per mole. So a better way to do this would actually be use log space, since we're traversing several orders of magnitude. And log space, I'm going to do this in a separate box because it's going to give us that error right there. Log space uses these arguments as powers of 10. So if we go 1, 5, 5, we're saying we want to start at 10, we want to go up to 100,000, and we want 5 increments. So if we just take a look at B, yep, see we start at 10, and then we go all the way up to 100,000 and only 5 increments. So the issue here is that we are saying we want 10 to the 10,000th power. That is not going to work. So to get around that, we simply use the log of this value. And then once, so 10 to the log base 10 of 1e4 is obviously going to be 1e4. And then we can do that here. And then that brings us to our next problem here. We can't use 0 as our starting volume because if you notice, V minus B, our volume can't be smaller than our excluded volume or the volume that the molecules take up. So we actually want to start a little bit bigger than B. So this term here won't be 0, and we're not trying to condense the molecules into a space smaller than the actual volume those molecules take up. So we can say we just want to use we'll start with 1% over B. And then T for now, we'll just say is 300. And then from there, we can make our subplots. Add our data. And again, we want our x-axis to be our volume. We want our y-axis to be our pressure. And of course, we actually have to use this function here. So we're going to use cubic, or our pressure is equal to the result of using our cubic equation for pressure, and with the temperature T defined right here, and the volume defined above that. So if we take a look at our plot now, first thing you'll notice is that it absolutely sucks, and that is because our scales are not quite right. So it's relatively simple to update our axes to make it look better. We just use the update function, and we're going to start with the x-axis. And of course, we want it to be logarithmic because we're traversing several orders of magnitude. And we can do a similar thing with the y-scale. Normally, we would use trial and error for this, but I already know some good values for it since I've done this several times. So we'll go negative 250 E6 all the way up to 250 E6 pascals. Oh, I forgot to actually use the range here. Try that again. All right, and you can see our plot looks much, much better. So the next step here is to actually add more isotherms to it. So one more small thing, we actually changed this to -2 here because before we had MP log base 10 of 1E4. So if we take a look at that, our x-axis is a lot longer than we really need it to be, so we shorten that to -2, 1E -2. And since we're using powers of 10, we don't really need this log function here. We can just say -2. I forgot to remove a parenthesis here. Now our plot looks much, much cleaner. So now we can start doing this for a bunch of different values of T. And I'm going to go ahead and make some space here. So the way that we're going to do this, first off, we need to make our subplots before we do any of this other stuff. And then we want to use a bunch of different values of T using a certain increment. So we'll do for T in range, and we'll start at 275 Kelvin, go up to 800 Kelvin, and we'll use increments of 25 Kelvin. This will actually reach 775. It won't reach our final. So we'll have, what would it be? We'll have 20 isotherms plotted on here when we're done. And for each of those values of T, we want to calculate pressure using that T and then all these specific volumes given by this log space function. And then of course, for each of those, we want to add a scatter plot. So let's take a look at that. And here you can see all of our isotherms here. Accidentally zoomed in too much. Don't know how to zoom back out. But I'm going to cut away here and we'll come back after I learn how to zoom out. So we're technically done here, but we can do one more thing to make this a little prettier. So right now each of these lines are labeled trace 0, trace 5, trace whatever. And it's a little hard to tell, well, it's really hard to tell what temperature each of these are at. So we can just add a short little name here. And we want our temperature to be the temperature that we are currently at in this range here. And then that is, of course, in Kelvin. So if we go ahead and do this one more time. Here we can, when we hover over it, we can see what temperature we're at, and then we can see what pressure and what specific volume we're at. So that's how we can plot some isotherms for water using the SRK equation of state over a range of different t values.